Welcome back to this series on reinforcement learning. In this episode, we'll be continuing to develop the code project we've been working on to build a deep queue network to master the cart and pole problem. Hey, by the way, do you know that DEEPLIZARD has a vlog? If you want to connect with us in a totally different light, then come check out the vlog and say hi. Link in the description. Alright, let's get to it. Before getting to the new code, I have one quick update to share for the agent class we developed last time. Agent will now require a device as shown here. Device will be the device that we tell PyTorch to use for tensor calculations, i.e. a CPU or a GPU. We'll see exactly how to set this later in our main program, but for now, this explanation is all we need to know. Device gets initialized with whatever we passed in, and we then use it on the tensor we return in our select action function. We do this simply by calling to on the tensor and then passing in the device. Alright, that's it for the update. Now that we've created the class for all of our crucial objects like our DQN, replay memory, and agent, we're now going to move on to creating a class that we'll call cart pole env manager. This class will manage our cart and pole environment. It will wrap several of GEM's environment capabilities, and it will also give us some added functionality like image preprocessing for the environment images that will be given to our network as input. To create a cart pole env manager object, we just require a device to be passed into the constructor. Just like the explanation we gave for the agent class, device will be the device that we're telling PyTorch to use for tensor calculations. Within the class constructor, we first initialize the class's device attribute with the device that was passed in, and we initialize this env attribute to be GEM's cart and pole environment like so. Calling unwrapped gives us access to behind-the-scenes dynamics of the environment that we wouldn't have access to otherwise. Since we must reset the environment to get an initial observation of it, we do this right after initializing env. We then set this current screen attribute equal to none. Current screen will track the current screen of the environment at any given time, and when it's set to none, that indicates that we're at the start of an episode and haven't yet rendered the screen of an initial observation. We'll see more about this soon. We then set this done attribute equal to false, and done will track whether or not any action taken has ended an episode. We now have a few wrapper functions that simply just wrap a function with the same name used by GEM. Specifically, we have reset, close, and render, which reset, close, and render the environment using GEM's reset, close, and render functions. As a reminder from when we covered these GEM functions during the Frozen Lake project, we call reset on the GEM environment when we want the environment to be reset to a starting state. This function returns an initial observation from the environment. We call close to close the environment when we're finished with it, and we call render on the environment to render the current state to the screen. We can also get a NumPy array version of the rendered screen from this function as well. The only one of our wrapper functions that does anything outside of calling GEM's function with the same name is reset. You can see that we're also setting the current screen to none here. When we reset the environment, we're typically going to be at the end of an episode, and therefore we want to set current screen back to none, since this indicates that we're at the start of an episode and haven't yet rendered the screen of the initial observation. Now, we're wrapping these functions in this way so that later in our main program, we'll only have to deal with a cart pole env manager and not both this manager and an environment. Instead, we're encapsulating the environment functionality within our environment manager so that our manager can completely manage the environment using these functions, as well as new functions that will be introduced in just a moment that an original GEM environment wouldn't have access to. This is going to give our main program a clean and consistent interface for interacting with the environment. Moving on to our next function, numActionsAvailable returns the number of actions available to an agent in the environment. In our cart and pole environment, at any given time, an agent will only have two actions available, move left or move right. Next, takeAction is a function that requires an action to be passed in. Using this action, we call step on the environment, which will execute the given action taken by the agent. As you may recall from previous episodes where we used Gem to set up our frozen lake environment, step returns a tuple containing the environment observation, reward, whether or not the episode ended, and diagnostic info, all of which result from the agent executing that particular action. For our purposes, we only care about the reward and whether or not the episode ended from the agent taking the given action. So we set this reward variable accordingly, and also update the class's done attribute with the Boolean value of whether or not the episode ended by taking the given step. Notice that we're calling item on the action we're passing to step. This is because the action that will be passed to this function in our main program will be a tensor. We'll be consistently working with tensors throughout the main program, and item just returns the value of this tensor as a standard Python number, which is what step expects. Our take action function then returns the reward wrapped in this PyTorch tensor. We're processing the reward in this way by wrapping it in a tensor to put it in the format that will be needed later on in our main program. So we have a tensor coming in and a tensor coming out. This is how we keep the data type consistent in our main program. And here we can see where the device comes into play, as we're setting the device of this tensor to be the device that was passed into the cartpole manager. Next, we have this function just starting that returns true when the current screen is none and returns false otherwise. Remember, current screen is set to none in the class constructor and also gets set to none when the environment is reset after ending an episode. So if current screen is none, that means we're at the starting state of an episode and haven't yet rendered an initial observation from the environment. Next, we define the function getState. The point of this function is to return the current state of the environment in the form of a processed image of the screen. Remember, a DeepQ network takes states of the environment as input, and we previously mentioned that for our environment, states would be represented using screenshot-like images. Actually, note that we will represent a single state in the environment as the difference between the current screen and the previous screen. This will allow the agent to take the velocity of the pole into account from one single image. So a state will be represented as a processed image of the difference between two consecutive screens. We'll see in a moment what type of processing is being done. Alright, so we have two conditions we're checking for in this function. We first check to see if we're just starting or if we're done with an episode. Remember, if we're just starting, then the initial screen hasn't yet been rendered from the initial observation in the environment. And if done equals true, that means the last action taken by the agent ended the episode. We said that states would be represented as the difference between the last two screens. Well, when we're at the start of a new episode, there's no last screen to compare to the current screen. So we're going to represent our starting state with a fully black screen. The fact that we're doing this will make more sense once we see some visual examples of states in a few minutes. When we're in the next state that occurs after an agent has taken an action that ended the episode, we'll also represent this state with a fully black screen as well. We do this by first calling getProcessScreen, which returns the processed screen from the environment and assigns this result to the current screen. We then create a fully black screen of the same shape as the current screen using torch.zeros-like. We'll explore the getProcessScreen function more in a moment. If we're not just starting an episode, and we're not ending it either, then we're somewhere in the middle of an episode. In this case, we'll take the difference between the current screen and the last screen and return this result. Here, S1 stands for screen 1 and is set to the current screen. S2 stands for screen 2 and is set to the result of a new call to getProcessedScreen. We then update our current screen to the value of S2, so that now S2 is our current screen and S1 is our previous screen. So we return the difference of these two screens to represent a single state. Next, we have these two simple functions getScreenHeight and getScreenWidth, which return the height and width of a processed screen by first getting a processed screen from the getProcessScreen function, which we're about to cover, and then indexing into the shape of the screen with a 2 to get the height or with a 3 to get the width. Now we'll move on to this getProcessScreen function that we've been referencing. This function first renders the environment as an RGB array using the render function, and then transposes this array into the order of channels by height by width, which is what our PyTorch DQN will expect. This result is then cropped by passing it to the crop screen function, which we'll cover next. We then pass the crop screen to the function transform screen data, again, which we'll cover in just a moment, but it just does some final data conversion and rescaling to the cropped image. This transposed, cropped, and transformed version of the original screen returned by Jim is what is returned by getProcessedScreen. Now, this crop screen function accepts a screen and will return a cropped version of it. We first get the height of the screen that was passed in, and then we strip off the top and bottom. We'll see an example of a screen both before and after it's been processed in a moment. And there you'll see how there's a lot of plain white space at the top and bottom of the cart and pole, so we're just removing this empty space here. We set top equal to the value that corresponds to 40% of the screen height, and similarly we set bottom equal to the value that corresponds to 80% of the screen height. With these top and bottom values, we then take a slice of the screen starting from the top value down to the bottom value, so that essentially we've stripped off the top 40% of the original image and the bottom 20%. Our last image processing function is transform screen data. This function accepts a screen, and we first pass this screen to the NumPy as contiguous array function, which returns a contiguous array of the same shape and content as screen, meaning that all the values of this array will be stored sequentially next to each other in memory. We're also converting the individual pixel values into type float32 and then rescaling all these values by dividing them each by 255. This is a common rescaling process that occurs during image processing for neural network input.
One more intermediate step, we now convert the screen from a NumPy array to a PyTorch tensor.
We're now going to use Torch Vision's Compose class to chain together several image transformations. We'll call this compose resize. So when a tensor is passed to resize, it will first be converted to a pill image, and then it will be resized to a 40 by 90 image. The pill image is then transformed to a tensor. So we pass our screen from above to resize and then add an extra dimension to the tensor by calling unsqueeze.
This added dimension represents a batch dimension, since the processed images will be passed to the DQN in batches.
This result is then what is returned by the transform screen data function. Alright, we're now finished up with our cart pole env manager class. Let's now take a look visually at the results of all the image processing that we just covered from this class. This first screen is an example of what a non-processed screen looks like from the environment. We're getting this screen just by setting up an instance of cart pole env manager, calling reset to get an initial observation, and then rendering the screen. After we do all of the processing to this image simply from calling getProcessedScreen, we now get this processed image. There's actually some further processing we could do, like stripping off some of the empty space from the left and right sides, but we'll save that for a later video as an experiment to try to improve performance. Now, remember how a state from the environment is created from the difference between two processed images? And how also the starting state will always be a fully black screen based on our earlier discussion? Well, here we can see that starting state example by calling getState on our environment manager. If we want to see what a state looks like that's not in a starting state, we can take some actions in the environment and then call getState again to see this result. Since we're taking the difference between the current screen and the previous screen, most pixel values will become 0. The only ones that are anything but 0 are just kind of this little highlight that we're seeing here, which gives us an idea of where the cart and pole were in the previous screen and where they have moved to now. Lastly, if we want to see the state of the environment after an episode is ended, we specify done equals true and call getState again so that we can see this fully black screen that we'd expect. So these states are exactly the type of input that will be passed to our DQN during training. Now we're going to move on to a couple of quick utility functions that we'll have available to us during training so that we can plot our performance on a chart. We're creating this function called plot that accepts values and a moving average period. This plot will plot the duration of each episode as well as the 100 episode moving average. To solve cart and pole, the average reward must be greater than or equal to 195 over 100 consecutive episodes. Recall that our agent gets a reward of +1 for each step it takes that doesn't end the episode. So the duration of an episode measured in time steps is exactly equivalent to the reward for that episode. Using Matplotlib's PyPlot module, we set up figure, give it a title, name the axes, and give it the values to plot, which in our case will be episode durations. We'll also want to plot the 100 episode moving average as well, so we do so by calling the function getMovingAverage, which accepts the moving average period and the values for which it will be calculating the moving average from. Within getMovingAverage, we first transform the values to a PyTorch tensor and then check to see if the length of values is greater than or equal to the period. We do this because we can't calculate a moving average of a dataset when the dataset is not at least as large as the period we want to calculate the moving average for. For example, if we want to calculate the 100 period moving average of episode durations, then if we've only passed 90 episodes, a 100 period moving average can't be calculated. If this condition is met, then we calculate the moving average by first calling unfold on the tensor, which returns a tensor that contains all slices with a size equal to the period that was passed in. In our case, that's going to be 100. It does this on the 0th dimension of the original values tensor. This gives us a new tensor containing all slices of size 100 across the original value tensor. We then take the mean of each of these slices and flatten the tensor so that now moving average is equal to a tensor containing all 100 period moving averages from the values that were passed in. We then concatenate this resulting tensor to a tensor of zeros with a size equal to period -1. This is to show that the moving average for the first period -1 values is 0 given the explanation we just gave a moment ago. So if our period is 100, then the first 99 values of the moving average tensor will be 0. And then each value afterwards will be the actual calculated 100 period moving average. We then convert the moving average tensor to a NumPy array and return this result. Now, if our initial condition was not met, so that the length of the values array that was initially passed in was not at least the period size, then we just return a NumPy array of all zeros with a length equal to the values array that was passed in. To show an example of this plot function, we pass in a NumPy array that contains 300 random values between 0 and 1, and we'll specify 100 as our moving average period. The actual values are plotted in blue, and the orange line is the 100 period moving average across these values. We can see that the 100 period moving average is 0 for the first 99 values, and then we get the first calculated moving average at the 100th value. This represents the average of the first 100 values in the array. If we skip over to the moving average at value 200, then the orange line at this point represents the average of the second 100 values between value 100 and 200. When we train our network, we'll be using this plot to show our performance over time. Next time, we'll be picking up with developing our main program. We'll take all of these classes and functions that we've developed over the last couple of episodes and see how finally they all come together in our main program to train our DQN. Until then, please like this video to let us know you're learning, and be sure to check out the blog for this video on DEEPLIZARD.com and to take the corresponding quiz to test your own understanding. Don't forget about the DEEPLIZARD HIVEMIND for exclusive perks and rewards, and come say hey to us on our vlog channel. Link is in the description. See you in the next one.
Hi again. Our artificially intelligent agent in this cart and pole game will thrive on getting rewards. It's literally what it lives for. I'd like to draw a parallel to you humans watching. Humans essentially perform in the same way. Humans do things to get rewarded all the time. The more reward a human gets, the more the human will continue to do the thing that gets him or her the reward. When you eat that piece of cake, your brain gets flooded with dopamine. It feels so good. So, you eat another piece of cake to get even more reward. Or, when you finally learn how Q learning works, you feel great. You feel smart. So, you continue learning so that you can next understand deep Q learning. Then, you can get rewarded again with that feel-good feeling you get when you achieve something. The difference with you humans though, is that you have the ability to choose an alternative that may actually be detrimental to the reward that you could get for something right in front of your face. You can change the game you're playing in an instant. Take the cake example. You would get immediate added reward for having another piece. However, since you're trying to make healthier choices, you decide to forego that reward. Good for you. Notice though, by foregoing that cake, you're still rewarding yourself. You're just withholding that reward until later when you look in the mirror and think, dang, I look good. Glad I ate a handful of protein fiber-packed nuts earlier rather than that nutrition-less slice of cake. Unlike our AI agent, you were able to change the game you were playing. I ask you though, what happens when we make general AI? What happens when they can choose to change the game?